I will begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have just to meet together and to study your creation. Just pray that you'd be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so today we talk about isometries. So, definition. If you have phi from U to V, all right, a diffeomorphism which means it's smooth with smooth inverse, right? And this is a diffeomorphism between two Riemannian spaces. So pair U with metric G1 and pair V with metric G2, all right? Then phi is an isometry, all right, if the pullback under phi of G2 is equal to G1. All right, so what that actually means, when you write this out in detail, what does that actually mean? That actually means that G1 of P, acting on vectors xp, yp, is equal to G2 at phi of P, acting on the push forward of xp and the push forward of yp. So in some sense, I mean not in some sense, this means that phi is a diffeomorphism which preserves the metric structure, right? So the concept here is that these two Riemannian spaces really have the same differential geometry. Okay, they have the same metrical properties. Now, so let's look at his example. So he starts out small. He says, let's look at U and V both being R2. And he says, let's look at G1 equals to G2 equals to dx tensor dx plus dy tensor dy. All right. For most things we've been doing lately, when you do this, it's kind of nothing interesting happens. Well, that's not entirely true. Like we reproduce the ordinary parallel transport or whatever, you know. But this is a little more interesting. So when you, if we have phi, let's suppose is equal to, you know, phi1, phi2, right? So what would, let's see here, we want to calculate the pullback. We want to calculate the pullback of G2, right? It doesn't mean pullback of whatever it is anyway. So, so it's phi pullback dx tensor dx, right? Plus phi pullback. Hey, excuse me. So what's that look like? Remember, properties of pullback, that's the same as d of phi pullback x tensor d phi pullback x, right? And likewise for the y. You don't really need to write this all out if you don't want to. I'll get to the point here in just a second. What are those? That's nothing more than the first component function of phi, because when we take the pullback of a function, it's just composition, right? So this is literally d phi 1 tensor d phi 1 plus d phi 2 tensor d phi 2. Which we can express, of course, as partial phi 1 partial x dx plus partial phi 1 partial y dy tensor. Man, I really want to write square right now, partial x dx, but I'm resisting. Right? And then likewise, with 1 change to 2. So we multiply that out, what do we get? We have phi 1 partial x quantity squared, right? Plus phi 2 partial x quantity squared. That's on our dx tensor dx, right? I'm collecting them from both terms. What else is there? There's the xy, which is what? We've got partial phi 1 partial x partial phi 1 partial y plus partial phi 2 partial x partial phi 2 partial y dx tensor dy. And then also partial phi 1 partial y partial phi 2 partial x plus partial phi 1 partial x partial phi 2, or rather partial y, partial phi 2 partial x dy tensor dx. And then finally, sorry, my formatting's a little bit weird, but you guys got it, right? The dy terms gives me partial phi 1 partial y squared plus partial phi 2 partial y squared, right? Dy tensor dy. Now, in isometry, right, it's supposed to do what? That's supposed to be equal to G1 again, right? Which in this case is dx tensor dx, right? Plus dy tensor dy. So what equations do we get? So you can equate coefficients, right? You get partial phi 1 partial x squared plus partial phi 2 partial x quantity squared equals to what? There's a 1 here, right? We get likewise partial phi 1 partial y squared plus partial phi 2 partial y squared equals to 1. And what else do we get? We get the other ones are 0, right? So partial phi 1 partial x partial phi 1 partial y plus partial phi 2 partial x partial phi 2 partial y equal to 0, and also partial phi 1 partial y partial phi 2 partial x. Was that supposed to be a... No, it's 1, 1, and... Is it really 1, 1, 2, 2? And then 1, 2, 1, 2? Or do I have something wrong there? Yeah. Thank you. Partial phi 1, partial y, partial phi 1, partial x plus partial phi 2, partial y, partial phi 2, partial x. All right. Ay, ay, ay. Okay, so there you go. Those are the conditions to have an isometry of the plane. Let's see, or maybe this is easier if we look at, maybe helps to say partial phi 1. I mean, to look at the Jacobian of phi, which would be what? Right, so these equations, and then, that's, so my equations are actually what? They're a squared plus what? A squared plus c squared equals to 1, right? And they're, what are they? Say again? B squared plus d squared equals to 1. And these are what? Oh, they're the same equation twice. Let's see here. What if we did? So the question is, like, what kind of matrix solves those equations, So let's see here. If we have, try that here. Suppose, just to show you what is a solution, I think if we have AD minus BC equals to 1, if the determinant was 1, suppose that was true, then if we have A, B, C, D, and multiply by D minus B minus CA, this would be the inverse of that given this condition, and that would give us AD minus BC, and well, I'm sorry, I know what it's going to work out to what? That's going to work out to, yeah, the identity. I'm sorry, I'm not sure what I'm doing.
Can we say let A equals sine alpha, C equals cosine alpha, B equals sine beta, D equals cosine beta?
Oh, there you go. That's better. That's better. So what did you say?
So A and C are sine cosine alpha, and B are cosine cosine beta, and then look at the third equation.
You said A equals to, what is it? Cosine?
Yeah, either way.
Cosine alpha D equals to cosine alpha? Oh, cosine beta.
I don't know. We'll probably end up eliminating one of those.
Well, what if D was cosine alpha? And what if C was equal to minus sine alpha?
C would have to be
And what if B was equal to sine alpha? Would that work?
no, C has to be positive sine alpha.
It does?
Oh. That's right. Okay.
See, then certainly A squared plus C squared is 1. B squared plus D squared is 1. Thank you, guys. And then this works out to 0, doesn't it? Because we've got cosine plus sine, cosine times sine plus minus cosine times sine. So these are satisfied. Yeah. think he actually has some details. I was just playing. So of course he, on page 248, he works out, he gets to these, all right? And, oh, that's where he stops. But he does point out, if, all right, if phi is linear, right? If phi is a linear map, in other words, phi of x comma y equals to a, b, c, d times x, y, right? So if phi is linear, then in fact it must be, I mean, that literally, I mean, these partial derivatives actually literally give us a, b, c, d, which then forces, this isometry condition actually forces us to have an orthogonal transformation. Yeah, so what he says is, hence, the system of PDEs that defines Euclidean isometries agrees in the linear case with the classical fact of linear algebra that orthogonal matrices are exactly the linear isometries of R2. Now, you guys have suffered through something deeper, which is if you look at the distance-preserving maps on the plane, in fact, there is only affine maps. So actually, what he doesn't say in here is that, oh, by the way, if you look at the Euclidean distance between points on the plane, and you look at maps that preserve the distance between points, there's only two kinds of maps that do that. They're translations, and there's three. There's translations, there's rotations, there's reflections, and then compositions of those give us the so-called rigid motions in the plane.
We did that in abstract.
Yeah, that was a problem that I gave you guys in abstract. That's probably the hardest problem I've given you this semester. Yeah.
Other than the one I had to write a program to solve.
Yeah, the one you had to write a program to solve. That's funny. The next example. So the larger point here, guys, is that, and what he's looking at right now is what's called the self-isometry, right? The question is, what maps of the space back to itself preserve the metric? Okay? A little bit later, he proves that these form a group. See, because if you take the composition, suppose you have an isometry that preserves the metric. If you take if you have an isometry from the space to itself, and you take another isometry from the space to itself, then you compose those two, you get another isometry from the space to itself. Take the inverse, you get an isometry from the space to itself. Right? The identity is an isometry from the space to itself. So you get a group of mappings, right? In fact, a group of permutations on the space that preserve the metric. These form a group. They do have a name, I'll tell you. I'm not sure he gives it though. I'm not sure it's called the isometry group of the manifold. Excuse me, it's the isometry group of the Riemannian space. I mean, manifold, you could think about a manifold with lots of different metrics. So a Riemannian space is a manifold plus a metric. It's more structure. Another example he gives is the half plane, which you guys have had lots of homework on, or you're about to have homework on, depending on where you are in your work. But anyway, this guy with the metric, the Poincare metric, 1 over y squared dx tensor dx plus dy tensor dy. All right? And he shows, what does he show? He shows that the mapping phi of x comma y equal to minus x over x squared plus y squared and y over x squared plus y squared. He shows that this is an isometry. In other words, that phi pulls back g to g. In that sense, it's a self-isometry of the Poincare, the half-plane with the Poincare metric. Now, we could go through the calculation, and maybe it's worthwhile. I'll tell you what, I'll at least start it. So what's required here? How would we do that? We basically need to calculate the pullback of g, right, under phi. So if you'll allow me this slight abuse of notation, what that looks like is well, this isn't, I have not abused notation yet, but I will, rest assured. It's that times, well, you know what it is? It's really d phi 1 squared plus d phi. Now this is a physicist notation right here. But by that square, I mean the tensor product of d phi 1 with itself and d phi 2 with itself. That's a tensor square. Now the pullback of y squared, right? Excuse me, the pullback of 1 over y squared is what? It's 1 over y over x squared plus y squared, right? And then I'm supposed to multiply d phi 1, which is, yeah. All right. What is d phi 1 here? Can you take the part? What's the total differential of that? Let's start out here. What's the x derivative of this? So we've got minus 1 times x squared plus y squared minus x times 2x divided by x squared plus y squared squared, which is minus 3x squared minus y squared, if I haven't made a mistake. No, I think I've made a mistake. Tell you what, I'm going to write down what he has here and stop being an idiot. So he calculates x squared minus y squared for that one. So I've got a sign error. Can you see it, where it is? I've got 3, he's got minus 1. Plus 2x, see here, this is a plus. Yeah, because minus a minus is a plus, right? Yeah, okay, great. And so that's dx plus 2xy over x squared plus y squared squared dy. Now, you square that in the tensor sense, and then the d phi 2 is minus 2xy dy over x squared plus y squared squared plus x squared minus y squared over x squared plus y squared squared. That's not a dy, that's a dx. That's a dy. That squared. It looks so small on the page. You know? It looks very small, but it, yeah. Now you can kind of see what's going on here, right? Do you see what I see what's happening with the denominators. You notice you've got an x squared plus squared here, 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 here and here in the reciprocal sense, so those just cancel. And then you've got like 1 over y squared, and you're going to get an x squared minus y squared squared dx tensor dx, right? Plus other stuff. And then from this term, we get a what? We get a 4x squared y squared dx tensor dx, right? Plus other stuff. I'm just focusing on the dx tensor dx piece because I've lost patience for the rest. And so when you square this out, what happens?
Denominators don't have x squared plus y squared to the fourth, whereas on the left we have x squared plus y squared, which is squared. We have the tensor squared.
Oh, right. Curses. Well, I guess I would have come to terms with that soon enough. But you are correct. So we still have a residual x squared plus y squared everywhere, right? Squared? Oh, yes, you're right. And there, right in a nutshell, is the danger of suppressing that in a nutshell is the danger of this notation, among other things. You gotta be really careful with that kind of notation because you'll do that kind of thing. Anyway, 1 over y squared. And so that's going to give us a, x to the fourth minus 2x squared y squared plus y to the fourth, right? Plus 4x squared y squared divided by x squared plus y squared squared dx tensor dx plus other terms. But you see what happens. The 4 and the minus 2 conspires to give you a 2, which gives you an x squared plus y squared squared. They cancel, and it just leaves you 1 over y squared dx tensor dx. And then plus, of course, we're also going to get 1 over y squared dy tensor dy if we do the other 75% of the calculation, right? Again, it looks so small. Looks like it looks so small. But there you go. That's pretty neat because can you recognize what this function is? What is this isometry? Let me put it in complex notation. This function is phi of x plus iy equals to minus x plus iy divided by x squared plus y squared. So what is it? See, it's minus 1 over z. Yeah. Okay, so generally finding the global isometries of a Riemannian space is very difficult. There are spaces that are so unsymmetrical, let's say. They're so kind of ugly that the isometry group just collapses to the identity. That can happen. But what's more fun, what's more interesting is if you can study a Riemannian space where the isometry group actually has mappings in it. When you have mappings in the isometry group, when you have a group of isometries to work with, you can do things with those. You can study the geometric structure in an interesting way using these isometries. That's essentially the idea of Klein, I guess, is to study geometry by its transformations. But here's a theorem which extends our purview a little bit here. If we have U and G, a Riemannian space, all right, and if we have X is a vector field, such that the Lie derivative along x of the metric is equal to 0. All right? Then, for each p, all right, in U, the flow phi sub t, from u sub p to phi sub t of up, all right, generated by x, what is it then? Well, remember what we learned is that generically speaking, the flow generated by a smooth vector field is a diffeomorphism, right? It's a local diffeomorphism. It won't give you a diffeomorphism of the whole space, but it'll give you a diffeomorphism from like one little spot on your manifold to some nearby spot, right? So this is first, from what we already know, a diffeomorphism, but more than that, it's actually a isometry in the local sense. So a little bit more data, satisfying, so some fine print here. So suppose phi at time 0 of p is p, all right, and here's the integral condition, d dt of phi sub t of p is what? What's that supposed to be? What's the velocity of the flow at the point supposed to be? It's an integral curve, right? So it should be x of phi sub t of p. That's just saying that the flow lines up with the vector field, right? But this is a family of isometries. Meaning that the pullback under the flow of the metric is the metric again, for all such t that phi sub t is defined, you know? As we know, the flow doesn't have to go on forever. Sometimes it can't go on, right? There are other flows which go on for all time. It depends on the nature of the metric field, the vector field, right? So vector fields which have this property for a given Riemannian space are very special vector fields. They're called killing fields. Actually, I think they're called killing vectors. Killing fields sounds worse. Let's see here. Oh, a killing vector field. I put a vector between the fields, so it's not quite a killing field. That's good. I feel like we should be supporting killing fields here. Let's see here. Seems bad. Oh, where are we? All right. Stop that. Definition. A killing vector field is a vector field x, all right, such that the Lie derivative along x of the metric is equal to 0. These are also known as aka infinitesimal isometry. All right. That idea, he says, arises from the fact that we can integrate these vector fields to find isometries on them, on the space sometimes, or at least in a local isometry, right? Now, as is everything here, right? I hope you've noticed that differential equations are kind of married to manifold theory and differential geometry, right? Every interesting thing we do at the end of the day boils back down to some system of partial differential equations that we may or may not be able to actually solve for examples. And the same is true here. If you actually want to find the killing fields for a given metric, what do you have to do? It goes back to exercise 4.35, right? So when you actually exercise 4.35 tells you how to actually unwrap this monstrosity, right? This, in components, what's it look like? This works out to the sum, k equals 1 to n, of the x upper k partial gij partial xk plus gjk partial xk partial xi plus gik partial x upper k partial x sub j. All of that equals to 0 for what? For all I and j, right? So those are the conditions which the killing fields have to meet for a given metric. So about the only one we have the patience to actually sort through today, probably the Euclidean one, right? What are the killing vector fields for the Euclidean metric? At least we can do that one. So what's Gij for Euclidean metric? Delta ij, right? So if we consider the Euclidean metric, at least the first term is gone, right? 0 for Euclidean. And so we're looking at the sum delta jk partial xk partial xi, k equals 1 to, we'll do the plane, 2, plus delta ik partial xk partial xj, right? Can we simplify that? Yes, we can, because those Kronecker deltas kill the sum, and it just leaves me with partial x. I set j equals to k, so I get partial xj, partial xi. And over here, this kills the sum, and it sets the k equals to I. So partial xi, right, partial xj. So what do you get here? If we can look at different cases, right? We've got like I equals to j equals to 1, I equals to j equals to 2. What's that give us? Like partial x1 partial x plus partial x1 partial x equal to 0. And this one gives me partial x2 partial y plus partial x2 partial y equal to 0. So from I equals to j equals to 1 or I equals j equals to 2, we just get the condition partial x1 partial x equals to 0 and partial x2 partial y equals to 0, right? And then on the other hand, we could look at like I equals to 1, j equals to 2. What would that give me? Partial x2 partial x plus partial x1 partial y equals to 0. I think that's enough. We can solve it with that. We could, of course, also look at the, well, you notice that these are symmetric in I and j, right? So like looking at I equals 1 and j equals 2 versus looking at the other way around, they're going to be the same equation. So like this is it. But these are very nice. That says that x1 is what? Just a function of y, right? See this? This means that x1 is just a function of y. And this tells me that x2 is just a function of x, right? So then what does this says? But this, on the other hand, says that partial x2, partial x, is equal to minus partial x1, partial y, right? And what does that mean? Let's see, well, let's see here. This is what? Function of x, right? What's this one? It's a function of y. So that implies, the only way you can have a function of x and a function of y is when it's a constant. So this means that x1 is equal to a and x2 is equal to b. I think. Oh, I'm sorry. That's not quite accurate. I'm sorry. I'm misreading it. It says the derivatives, right? I should say this is equal to a. Okay, and so then integrating that gives me that x1 is equal to minus ay plus b, right? And x2 is ax plus c, something like that. And so the killing fields for the Euclidean had the following form: a y plus b partial x plus minus ax plus c partial y. Well, that's a good question. What is this exactly? Oh, well, anyway, the next thing he does is he integrates those. So then you can do what? You can find the flow. Uh-oh, it's a soprano. So you can find the flow of these by integrating them, and then he gets circles. Okay, that's on page 251. I won't go through it. Actually, he doesn't get circles. He gets circles. He also gets plus a term. So they're not circles concentric at the origin. They're circles that could be anywhere. And that's kind of the point, is the killing fields can generate rotations anywhere in the plane. They don't have to be concentric around the origin. Then the next thing he does is he calculates the killing fields for the Poincare. All right, and so for the Poincare, and I won't go through the details. I'll just tell you the outcome of it. Okay, for that one, we get for Poincare on upper half plane, we end up with the following equations: partial squared x1 partial x squared plus partial squared x1 partial y squared equal to 0, and likewise for x2. Can you recognize these? What are these? So what are the... He actually gives the killing equations 5.23, 5.24, 5.25. They're kind of interesting. I won't write them down. And he mentions that they imply, well, he gets these, from the other, I mean, he writes down the killing equations, all right? From the killing equations, he gets the following. So these are not the killing equations, but they're a consequence of the killing equations for the killing fields. I'm calling the equation, I just erased the killing equation. I don't know if it's actually called that, but that's what I'm calling it today, so hope you can forgive me for that. Let's see here. Although it's probably called the killing equation. Let's see here, x2. So these are conditions that you find for the killing. So you see it, Cooper? What are these? No, these are just the regular Cauchy-Riemann equations. If we let x1 equal to u and we let x2 equals to v, you'll recognize them more. This first one translates back into ux equals to vy. And this one translates after you write it as the other way around. That's uy equals to minus vx. And these, of course, are Laplace equations. So the killing fields for the upper half plane of the Poincare metric tie into study of harmonic functions. And in fact, the components to the killing vector fields, they'll actually appear as like harmonic conjugates to a particular complex function. So anyway, I think it's really interesting. And move along here. Make sure I don't run out of time. I got some things to say today. Oh, yeah, be careful. So I hope I've done enough of this that you could fill in the gaps where I haven't gone through it. I think you can. I think we have probably done enough pullbacks that you're starting to get the hang of it. Let's see here. Do you guys have any questions about what I said about the set of isometries on the space being a group? I don't need to write that out, do I? That makes sense. So, now this next theorem is interesting. Let me just tell you what he eventually tells us. Much later in the section, he fesses up to what all of the come on. Much later. Like almost at the end. Come on, where'd you go? Dude. Eventually. So eventually, at the very end of this section, he tells you that if you look at the upper half plane of the Poincare metric, and you look at any isometry, it has the following form. It can be written as the composition of a fractional linear, a Mobius transformation on the complex plane with something like, has the formula phi of z is az plus b over cz plus d. Complex conjugation, z bar. Oh, did I? No, I don't need a z bar there. It's either a Mobius transformation or complex conjugation, or minus complex conjugation, depending on whether you have the determinant is positive or negative for your isometry. The Jacobian, of course, and he points you to a reference where you can read more about that. On the other hand, the isometries of the Euclidean metric are what I already told you about. They're a composition of translations, reflections, and rotations, right? So I thought that was nice that he actually he gives you these particular examples of isometries for the Poincare metric, but he actually does complete the thought at the end of the section, which is beautiful. He also does not tell you how to prove that. And I think that actually is a very interesting topic to work through that. But to work through that without the full force of complex analysis would be an unwise decision. By the way, this notion that the metric is constant along the flow of the vector, that's part of a more general lemma at the end of chapter 4, which I didn't say in here, but it's not really special to the metric. What's special is that when you're talking about the metric, it brings all the things that the metric touches on. and so forth. But here we go, theorem. This one's quite nice. Theorem 5.6.11. It has the following idea. If we have S is a subset of Rn, a geometric set, all right, and parametrized, all right, by phi1, which goes from U1 to S, and phi2, which goes from U2 to S, where U1 and U2 are subsets of Rk. So we're talking about a k-dimensional submanifold of Rn, right? And these are two different patches on that k-dimensional submanifold. And he supposes that he has a Riemannian metric G on Rn, all right? So he says, suppose Rn has metric G, all right? Well, I think of G as being restricted to S. That gives me an induced, sort of the natural induced metric on S as a geometric set, right? We can think about restricting G to S. That would give us a metric up there. But that's not where he goes here. He says define G sub I as the pullback under the ith map, the pullback under phi I of G. Okay, for I equals to 1 and 2, yeah. Thanks. Then phi, which goes from U1 comma G1. So here he's pairing the Riemannian space with its metric, okay? That's just a fancy notation for the set U1 paired with the metric G1, okay? To the set U2 given the metric structure, metric G2, that pullback metric there, defined by phi equal to phi2 inverse composed with phi1 is an isometry. I think the proof of this we can afford to do. So here we go. Phi, it must be really easy then. Yeah, you got me. Phi2 pullback G2, phi pullback G2 is phi2 inverse composed with phi1 pullback G2. How do we do that? Properties of pullback. That's phi1 pullback, phi2 inverse pullback G2. But that is so that is phi1 pullback, phi2 inverse pullback. What is G2? Well, G2 is phi2 pullback G, right? But then again, by properties of pullback, we can say, well, that's really phi1 pullback phi2 composed with phi2 inverse pullback G, right? That's the identity, so we just get phi1 pullback G, which is G1. So what we've just shown is that under this phi map, we pull back the G2 metric to the G1 metric, which is to say that phi is an isometry. Now this kind of seems like just parameterization gamemanship or something. I mean, it just seems kind of like a vain game, right? except when you actually look at what it means for examples. So here's an example of this into action. We have studied the paraboloid, right? So the paraboloid, which was the set S, right? Sets x, points x, y, z, such that z is equal to x squared plus y squared. And we had x was positive and 0 less than z less than 1. I guess we just added that to be specific. And so, of course, we can give R3 the usual Euclidean metric, dx tensor dx plus dy tensor dy plus dz tensor dz. So, on the one hand, we can look at phi1 of uv equal to u comma v comma u squared plus v squared. On the other hand, we can look at phi2 of r theta equal to r cosine theta, r sine theta, and r squared. So those are two different parameterizations of the paraboloid. The one is sort of the Cartesian parameterization. The second one is just the natural polar coordinate parameterization of the paraboloid, right? Because if you look at putting x equals to r cosine theta, y equals to r sine theta, you get z equal to r squared cosine squared plus sine squared, which is just r squared. But look at what happens when you compare the metrics here. The pullback metric. So, we set G. We set G equal to dx tensor dx plus dy tensor dy plus dz tensor dz, right? Don't worry, I won't actually do the calculations this time, but if we pull back under phi1, we've actually done this calculation a different day. Then we got the pullback metric of 1 plus 4u squared du tensor du plus 4uv du tensor dv, 4uv dv tensor du plus, you'll forget my formatting, 1 plus 4v squared dv tensor dv, right? So this goes up there. But anyway, so that's we talked about this pullback metric before, right? We calculate, in fact, we calculated the Christoffel symbols for that one. Pullback of this one, he works it out in here, and he gets the following. 1 plus 4r squared dr tensor dr plus r squared d theta tensor d theta. Now, I got to tell you guys, I just feel silly having spent the time we did to calculate the Christoffel symbols for the UV one, when I could just as well have used polar coordinates, describe the same geometry, because they have the same geometry, they're isometric, and that metric is diagonal, which is way, way nicer, right? So what he says is, basically what we're doing is we're giving two different models for the same Riemannian space. To me, the Riemannian space is the paraboloid, with the induced metric from R3, and these pullback metrics in the planar models, right? But